Hello YouTube, and welcome to my Impl PERTy YouTube series where we will be implementing the project review and evaluation technique in Rust, which has resulted in the crate PERTy that anyone can download on crates.io and use in their projects. In this video, we'll be just covering the basics of what PERT is and what you might want to use PERT for. So, the definition is the project evaluation and review technique is a method for analysing the activities involved in completing a given project, especially the time needed to complete each task, to identify the minimum time needed to complete the project. Okay? So that's all from Wikipedia. In essence, it's a graph-based technique where we have a series of tasks that we want to traverse. We have the dependencies between those tasks and the durations of those tasks, and we get the computer to solve and resolve how long is it likely to take to complete that project. So what can we get from it? We can get the start and end time ranges for completing tasks. We get the idea of float and slack between tasks, where you may have 10 weeks to complete a task when it only needs 5 weeks. We kind of identify that in the graph, so we know which ones are the critical and which ones are the non-critical tasks. And those are the critical ones are normally referred as critical tasks or activities, where there is no float, and that means that you have to get those completed on time if you want your project to complete as soon as possible. And the ones that are chained together are known as the critical path, those tasks that need to be completed in order to complete the task on time. So an example of this is provided here, and really the minimum data we require is an ID, so some kind of unique identifier for the task. More likely, of course, in any kind of task-based project structure, you'll have the team members that are going to be involved in those tasks, the resources required for that. And that's all kind of ancillary, additional metadata related to those tasks, not necessary for solving the PERT problem. Unless when we get to a bit more advanced kind of PERT techniques, where you look at the actual kind of dependencies between resources, where you've got constraints on the number of resources can be used. Nonetheless, at the minimal level, we have an activity ID, we have the dependencies between those activities and the links between those, and typically with PERT, we will use the PERT distribution estimate for the likely times, and we estimated time. Now that's based on 3 values: the optimistic, most likely, and pessimistic times for completing that activity. In reality, and we'll get to how we implement PERT, it is just we want a duration for each of those tasks, and we sample from a distribution. This one gives us a value, a constant value that we can use in our tasks, or we could use each task could have their own distributions. They could be uniform, triangular, whatever, binomial, whatever they may need to be to represent the uncertainty in the time it takes to complete a particular task in a project. But what you normally do if you're just using the typical version, you'd have your optimistic, most likely, and pessimistic times. You would then solve this equation for each of your tasks to get their estimated duration. And that's then your constant that you then feed into the PERT evaluation technique. So once you've computed the durations that you want to use for each of your tasks, we would then construct the graph. So given dependencies between the tasks, the ones that we had in that example, we would construct this graph where we would then populate the durations for each of those tasks within it, and then you can see in a manual way the dependencies between that. So you've got the starter project, where A and B then can occur in parallel. C then depends on A, D then also depends on A, F depends on D, E depends on B and C, G depends on E, and then all of that culminates at the end of project depends on G and F completing. So we construct this graph, and then the first step we do, or the second or the third step now, is to then compute the early start and finishes times. So it's a case of traversing this graph and going for each of the tasks, looking at the previous task that it depends on to identify the early start time. In the case of A and B, we can start as early as possible because the start project is 0 and it takes no time because we are just kicking off this project, and therefore A and B can start in time 0, and they take 5.33 and 4 units of time, whatever it may be. So therefore, the early finishing time is 5.33 and 4 respectively. We continue down this graph, we have C and D. These depend on A. So they take the earliest finishing time from A, which is 4. That becomes their earliest start time. We then add on their durations to get their early finish times. For the case of E, down here, we have it depending on B and C. So it needs to find the time that it can earliest start. So you have to look at either is it 5.33 for B, or is it C, and that's 9.17. As C is the latest of the two, that's the one that you take as the earliest start time. It actually has to wait on C before it can start here. And then of course you add its duration and on, and so on and so forth as we compute down this scale until we reach the end of project. That will give us our earliest finishing time for the entire project, which is here, is 19.51. Then we look at the latest times at which things can finish. So that's step 4, which is now we go back up the graph. We reverse and traverse back up the graph. So we take the end of project. We know that the latest time at which we finish, which then becomes our latest start and finish times, is 19.51. We then, it's a case of then subtracting the durations of the previous tasks to find their latest time at which they can start. So for G, we subtract 5.17 from 19.51, we get 14.34. And again, in a similar fashion as step 3, we traverse, looking at the latest times at which items can start. And then we go all the way until we get to the start of project. So then we get to a case of analysing. So now we've kind of populated the graph with all the numbers that we're interested in, and now we can start doing some analytics. And a typical one is to identify this critical path, identify the slack within the tasks, and the ability to move them around within a timeline. So what we can look at is the differences between the early and late start times. So if we start at the top again, let's say the start of project, we're looking at here the late and early start times, or it could be the early and so the times, and we're looking here for all the early and finished late times. We're looking for like basically a difference of 0, no slack. That has to happen within that timeline. Here, for example, we've got A, we've starred that, it's a critical activity because it has to start at 0, finish at 4. It also has 0 and finishes at 4 in the late finish times. There is no slack, no movement for A. And so the same goes with C, E, and G, and the end of project. In contrast, we have B, D, and F, which do have time between the earliest time it can start and the latest time it can start. For B, we have it as 3.84. It's because that's the difference there between the early and late start times. We actually have that time. We don't necessarily have to start B at the start of project. In reality, we can wait a bit before commencing that time, as long as we don't go beyond 3.84. Otherwise, it will then delay the project. So those are ones that have a bit of freedom, and maybe we don't have to monitor as acutely as the ones on the critical path, because any of the delays in this critical path means a delay for the entire project. And that's in essence the stuff that we can do with PERT. And here we've just done one example with one set of durations. If we were sampling these tasks over a series of durations, different distributions of durations, we can see how what's likely on the project on the critical path. It may change depending on where you sample in the distribution of the tasks. So you might do a Monte Carlo simulation to look at the ones that are most likely to be on the critical path, which ones come in and out of the critical path, and you can start, like you say, playing around with these numbers. You may have some ideas of resource, giving extra resource to a task that might shorten its duration. What effect would that have on the entire project duration? You can start to play around working where are the critical activities, where needs resourcing, how can we speed up, and maybe where are the bottlenecks in those projects. So that's PERT in a nutshell. And this series is all about implementing it in Rust. So we'll be looking at the trait system. And the idea is that this PERTy crate that I've created is that it's uses the trait system, so it enables users to construct their own task, structs, on which they can then implement a try into PERT task, which then gives us the necessary information to do our PERT analysis. Because most likely they'll want to create their own task structures that will have, those constraints or metadata about who's going to be doing that task, the resources needed on that task, all those kind of ancillary information, which is not necessarily needed for solving the basic PERT graph. It's going to be a single-threaded process, so I don't think these graphs, I intend that they'll get that big. Maybe one day, maybe we need to update the crate to be multi-threaded, but more so than often we'll be wanting to do Monte Carlo simulations. So the multi-threaded will be that actually we'll solve each graph on a single thread, but we'll do lots of those. So a kind of embarrassingly parallel task where we can then run hundreds of these on multiple threads, bring all the results together. So as we sample lots of different variations of that graph based on the distributions, the durations of each of the tasks within the graph. There's a lot there, quite nested there. And it's a graph structure, so we'll be using RC and RefCell there to be able to get the links. So we've got the kind of effectively node and edges. We'll be using RC and RefCell to connect effectively these tasks up and give us the ability to traverse this graph. So hopefully that's interesting to you, and I look forward to seeing you in the next one, where we will start our journey in implementing PERT in Rust. See you in the next one.